Predicted in Einstein's general theory of relativity, gravitational waves are disturbances in the curvature of spacetime caused by the motions of matter. Propagating at or near the speed of light, gravitational waves don't really travel through spacetime. It's the fabric of spacetime itself that's oscillating. Although gravitational waves pass straight through matter, their strength weakens proportionally to the distance traveled from the source. A gravitational wave arriving on Earth will alternately stretch and shrink distances, but on an incredibly small scale, by a factor of 10 to the negative 21st, or 1/60th, for very strong sources. That's roughly equivalent to measuring a change the size of an atom in the distance from the Sun to the Earth. The first test of Einstein's general theory of relativity was the bending of light by the gravity of large masses seen in the solar eclipse. It was made by a team led by Sir Arthur Eddington, who became one of the strongest supporters of the new theory. But when it came to gravitational waves, Eddington was skeptical and reportedly commented, "Gravitational waves propagate at the speed of thought." Eddington wasn't the only skeptic. Many physicists thought that the waves predicted by the theory were simply a mathematical artifact, but others continued to further develop and test the concept. By the 1960s, theorists had shown that if an object emits gravitational waves, its mass should decrease. Then, in the mid-1970s, American researchers observed a binary pulsar system named PSR 1913+16 that was thought to consist of two neutron stars closely and rapidly orbiting each other. Radio pulses from one of the stars showed that its orbital period decreased by 75 microseconds per year. In other words, the stars are spiraling in towards each other, and by just the amount predicted if the system were losing energy by radiating gravity waves. Gravitational wave astronomy could expand our knowledge of the cosmos dramatically. For starters, gravitational waves, though weakening with distance, are thought to be unchanged by any material they pass through, and therefore should carry signals unaltered across vast reaches of space. By comparison, electromagnetic radiation tends to be modified by intervening matter. Aside from demonstrating the existence of black holes and revealing a wealth of data on supernovae and neutron stars, gravitational wave observations could also provide an independent means of estimating cosmological distances and help further our understanding of how the universe came to be and the way it looks today and of its ultimate fate. Gravitational waves might unveil phenomena never considered before. From supercomputer simulations performed at NCSA and other advanced computational facilities, relativity researchers expect different types of cosmic events to possess characteristic gravitational wave signatures. Consider the waves emitted by a single distorted black hole, for example. The remarkable thing about a black hole when simulated on a computer is that no matter how it forms or is perturbed, whether by infalling matter by gravitational waves or via a collision with another object, including a second black hole, it will ring with a unique frequency known as a natural mode of vibration. It's this unique wave signature that will allow scientists to know if they've really detected a black hole. But that's not all. The signal will tell them how big the black hole is and how fast it's spinning.
And then finally, by the next century, we hope to have gravitational radiation detectors that would be able to capture the birth of the black hole itself or the subsequent collision of two black holes by the characteristic waveforms that are sent off, and those waves would be directly detected with these instruments.
Thank you for watching this video. I hope you enjoyed it. And if you have any questions about anything discussed here, just ask the question in the comment section of this video or send me a message. And if you have any questions about anything else regarding astronomy, again, just send me a message and I'll do my best to respond. Thank you.